It's very exciting to be here. So I'm Maithra. My talk today will be on do wide and deep neural networks learn the same things? This is based off of a paper of almost the same name with my amazing collaborators, Thao and Simon, and we're all like Google AI. So for this talk, I thought I'd actually first start off by giving a little bit of background and context as to what motivated us to look into this direction in the first place, and sort of some of our overarching research goals in pursuing this project, and some of the other directions we've been working on. So with that in mind, sort of really big step back, and I'll just say that as we sort of all know, over the past several years, the field of sort of machine learning has been just an amazing place to be in. We've seen these like incredible breakthroughs, starting all the way with speech recognition, and then computer vision, machine translation, more recently, more complex tasks like pose estimation and dialogue. And this has all really been made possible because of the rapid iteration and advancement of these deep neural network models on these specific competition benchmarks. So things like ImageNet and MS-CoCo in computer vision, benchmarks in machine translation, the GLUE, SuperGLUE, and SQUAD benchmarks in natural language understanding. There are a huge number of these. In fact, there are so many of these that there are sort of all these websites that are actually dedicated to keeping track of all the benchmarks we have and how the models and algorithms we're proposing are slowly getting better and doing well at all of these tasks. Okay, so that's sort of kind of field so far. And what's happened is that sort of all of this progress and development of these benchmarks has meant that looking forwards, we're able to push the boundaries of our field in sort of brand new ways. So we're seeing sort of two big sort of different pushes, I think. Firstly, we're seeing the development of models of sort of scale larger than we've ever had before, and sort of systems that are very complex in nature, have sort of many learned and moving parts, and are capable of tackling all kinds of like new tasks. So that's kind of one part. And then on the second side, we're also seeing just a huge amount of excitement from all of these different applications and domains in deploying these systems that we've been developing to deal with some of the key pain points in their domain. And this includes really high stakes applications, things like medicine and healthcare. So sort of summary is sort of looking back, things were exciting, and looking forwards, things also look really exciting for the field. But there's an important caveat here. And the caveat is that, if we want to continue pushing things forward in this way, we want to continue developing these sort of very complex models. We want to continue developing large scale systems. We want to be able to sort of safely and reliably deploy these systems in sort of these other domains. Then we have to be able to design very robust and sort of high quality models and algorithms. And that's where there's this gap. Despite all of the forward progress we've made, this design process for these machine learning systems is still sort of incredibly complex and involved. So say sort of, you're faced with this task of designing some new machine learning system. Well, that process is just so complicated. You're faced with like all of these different choices, ranging from the kind of model you should use to questions around the data, how you should train it, hyperparameters, and questions around the learning algorithm. And the big problem facing us is that we actually have to pick carefully amongst these choices to end up with a high quality, robust system. But at the same time, there's very little insight guiding what a good set of these choices looks like. So we end up with a design process that's pretty laborious and computationally expensive because people don't know what to do, so they try out a whole bunch of different things. And so they will literally build up this population of neural networks, each one which sort of has some specific set of design choices associated with it. And then the hope is that sort of amongst this population, there's something there that's doing what they want it to. Now this is the place where I think there's also this interesting gap between science and engineering. So on the engineering side, we have actually seen remarkable progress in sort of making this entire process much easier. From the development of sort of software packages to really help us to actually design, to actually write the code for these models better, to things like people here at Weights and Biases are doing in actually developing tools to sort of monitor and visualize these systems, to things that help us like navigate our compute architecture and load. But the place where I see a gap and where we need to catch up is sort of the science side of it. So in kind of measuring how sort of our models and deep learning systems are doing, we're still sort of falling back to these sort of metrics of like loss and accuracy, which are sort of historically inherited from this history of developing these systems on these competition benchmarks. And you know, that's nice, like that is a good place to start. But there's a limitation to how much these can offer us if we really care about principled design processes. So sort of most kind of obviously, these sort of loss and accuracy metrics are pretty much concentrated on what's happening at the very output, the very top layer of these deep learning models. Whereas sort of the bulk of the computation, the parameters, and the learning happens in sort of all of these hidden layers. And you know, we still have to kind of take steps. I mean, ideally what we want is sort of a suite of techniques that will let us understand what's going on there. Now, these hidden layers also pose challenges for us to analyze in this way. They're sort of large, they're complex, they don't have any kind of nice interpretable mapping. But the kind of questions that started us off sort of many years ago into this paper I'm about to present is just that we at least wanted to be able to take, you know, different members of our population and sort of understand how these different design choices were affecting their hidden representations. What's similar and what's different because of all these design choices we made? What's really going on? And sort of boiling this down, what we were really hoping to do is meaningfully compare hidden representations across neural networks. Now, this seems like a really fundamental question, but even sort of this fundamental question has some layers of sort of subtlety and complexity to it. And I don't know if I can do sort of full justice to it in the time, but I'll try and give some like some of the key things to think about when doing this. So first of all, there's this definitional question of how we actually should define a hidden representation. Normally we think of neural networks in terms of their parameters, but there's lots of redundancy in their parameters. So it turns out that a more effective approach is to actually think of the concrete outputs that a particular hidden neuron is emitting on some data set of interest, or sort of expanding this out to a layer. We can think of the representation of a layer as being represented by what we call an activation matrix. So sort of all of the outputs of all of its neurons on some data set of interest. And this sort of summarizes the representation learned by the layer. The other challenge in sort of comparing representations, which I'll just briefly mention, is sort of representations are distributed across neural networks. There's also no nice alignment. So whatever algorithm you come up with has to take all of those into account. So bearing these conditions in mind, in sort of work done a few years ago now, we proposed some of the first algorithms to actually do this in sort of a quantitative and reliable way. And we were able to use that to provide us lots of interesting insights about what's actually happening with these systems, how hidden layers are really converging, sort of the differences between networks that are sort of overfitting or memorizing versus actually generalizing well. And sort of building off of this, more recently, there was a paper that really advanced the core algorithm for performing these kinds of comparisons of hidden representations in neural networks. And so this algorithm is known as the CKA algorithm, and the way it works is it's going to take in two layer activation matrices, so some layer 1 and layer 2, and then it's going to map those into just a scalar similarity score. That's just simply telling us, well, sort of how similar are these representations. So 0 is they're totally different, and 1 is sort of they're identical. And this algorithm is going to be a very important lens for the question we're about to investigate. So going back to this kind of picture of design challenges, the question we really wanted to investigate is better understand sort of all of these different models people were playing with and sort of how the representations actually learned amongst these models might vary amongst them. And in particular, one trend that we're seeing as of late is that people are looking at actually playing with the total model capacity by varying the depth and the width of the model. So we've seen this across all kinds of imaging models, ResNets, ResNex, efficient nets, efficient dets, more recently transformers. And sort of two key hyperparameters people play with here are sort of actually changing the model depth and the model width. And oftentimes, you know, the resulting model is very performant, but we wanted to understand how these might be affecting the hidden representations, for which there are many open questions. So sort of concretely, are there any differences if we just look into a single model and sort of, look at what it's actually learning? Is kind of depth and width affecting that in any clear way? If we take models that look very different to each other architecturally, are they learning the same thing? And, are there even sort of characteristic errors that might be associated with these kinds of different neural network architectures? Those are some of the questions we were interested in. And so to study this, we turned to, sort of very simple setup. We took sort of ResNets, which are a family of models in image classification that have already, been in practice have sort of their depth and width varied. So we sort of took a family of models where we could kind of vary their depth and width in this way. And we looked at training them on these sorts of standard image classification tasks, things like CFAR10, CFAR100, ImageNet. And then sort of on these, using CKA as a lens, we went in to study what was happening in their hidden representations. And so in particular, CKA actually lets us, it's a very flexible tool and lets us compare any pair of hidden layers with each other. And so to represent some of the results, we kind of turn to showing things as a heat map. So what we have here is we have a neural network, and so along the x-axis we have sort of the layers corresponding to one neural network. Along the y-axis we have the layers corresponding to another neural network. And these might be sort of the same network, these might be different networks, these might be networks that have two different kinds of architectures. It doesn't really matter. We can kind of do all of these pairwise comparisons, and the plan is to sort of show it as a heat map. Sort of by convention, we sort of had the input in the kind of bottom left corner, so the output is sort of the top layer on the sort of the right and sort of upper half. And then for sort of any pair of layers that we could compare, we can just sort of go into their corresponding grid cell and fill it in with their CKA similarity score. Okay, so that's kind of like the schematic. Let's see what this actually looks like. So here are sort of two different ResNets. So again, along the end, so this time it's the model we're comparing is actually the same architecture. So both in the left and the right, we're taking the same ResNet model and sort of just comparing all of its hidden representations to itself. So along the x-axis, you have sort of all of the layers, and then along the y-axis, you sort of have the same layers. So in this heat map, yellow sort of colored is sort of maximal CKA similarity 1, whereas black is 0. Along the diagonal, you can, kind of reassuringly, you can see this nice yellow line, and that's because you're comparing each layer with itself. So of course, its representation is identical. If you kind of peer at this more closely, you can see other kind of cool artifacts from the result of this being a ResNet. So you sort of see this grid-like pattern, and that's because of the skip connections of the ResNet coming in. If you sort of stare even closer, you can see sort of like a 3-block styled structure, and that's due to the different stages that the ResNet has. Okay, so this is kind of, what things look like. But what happens to these heat maps as we vary depth and width? When we do that, the result is actually really striking. So this is kind of what happens when we vary depth and width. So the top row is what happens as we slowly make the architecture deeper. Bottom row is what happens as we slowly make the architecture wider. And what you can kind of really clearly see is what we call a block structure emerging in the representations. And sort of if you're following along, you'll sort of see that like kind of this block structure in words, what it really means is that we sort of have this large set of contiguous layers that have these really high CKA scores. So very high representation similarity. So that was really exciting. We went ahead and did some work to check this as a robust phenomena, things like that, and it does just very reliably appear in these sorts of wide and deep models. So this sort of suggests that this block structure maybe has some connection to the actual model capacity. And so we wanted to check whether this is really the case. Is there some interventional experiment we could do to really establish this connection? And one nice experiment you can do is you can increase model capacity artificially by reducing the training data set size. And so we went ahead and did this, and sort of, so as you kind of go down, like in each column, you're sort of decreasing the training data set size. And sort of, indeed, what you see is as you decrease the training data set size, you're sort of seeing this block structure emerge in models that didn't have a block structure in their representations anymore. So that was super interesting to see, and then sort of based off of this in the paper, we sort of did further analysis of all of this. But okay, so although so far, you know, we've kind of talked about like some of the motivation for the CKA algorithm. We've dived into the representations of a model, and we've seen that when we make them sort of wider or deeper, you know, performance-wise, they're still doing great, but their representations are getting this block structure, and this block structure is indeed linked with the actual capacity of the model. But to us, there was still a gap in sort of all of this, which is we still didn't understand sort of functionally what the block structure was really doing to the representations. So we were seeing this high representation similarity, but sort of layer by layer, what was really going on in the representations through the block structure? Okay, so how should we go about studying that? Well, if we take a few steps back and think about what we were doing with the CKA algorithm, what we were doing is we were taking these different layer activation matrices, and then we were sort of performing the CKA algorithm to compare them. And so instead, we went for something kind of even more low level. We looked at just studying the principal components of the layer activation matrix. And it turned out that a very important question to ask was, how important is the first principal component of these representations? And what we found is that the first principal component was extremely important for models that had the block structure. So what we did is you can sort of take the different layers of the network that's sort of shown in the x-axis, going from input all the way to output. And then you can, on the y-axis, you sort of have the fraction of variance explained. So for every single layer, we take sort of the fraction of variance explained by just the first principal component. And sort of what's really obvious here is you can see these two big sort of spikes. And these spikes actually correspond perfectly with where we're seeing the block structure when we do this sort of the CKA analysis. And in fact, if we then remove the first principal component of the representations, well, then the block structure is significantly reduced. So with this experiment and sort of others like this, we were able to really pinpoint the functional property of the block structure. So in these sort of high capacity models, the block structure worked to preserve and propagate the first principal component of these representations. So this is kind of a really nice summary of what was happening in the internals of a single model. And so sort of informed by this, we turned into the question that motivated us to start this paper in the first place, which was, well, what's happening in representations across models? Are wide and deep neural networks learning the same things? And it turns out to be a really good starting point to start by looking at a single model, because there's an important connection between the block structure and representations across models. So as the first simple comparison to see what was happening across models, we just looked at different random seeds. So now we're applying we're sort of computing these CKA heat maps, but these CKA heat maps are between models that are just different random seeds. So same architecture, but different random seeds. And there's this kind of important distinction between models that don't have the block structure and models that do. So with models that don't have the block structure, well, along the diagonal, we're actually comparing sort of the model to itself, no block structure here, but most importantly, in the off diagonal, where we're sort of comparing models of different random seeds, you can actually see there's a decent amount of similarity. In fact, between the same random seed and different random seeds, there's, it looks pretty similar, except for sort of this strong diagonal line, which is because in same random seeds, it's identical representations. So sort of in summary, we're actually seeing similar features across these different seeds. But when models have the block structure, the story is different. So of course, across the diagonal, you're sort of seeing this nice block structure, but in the off diagonal, you're seeing this big sort of lack of similarity, pretty much precisely where the block structure is. And so sort of put another way, the block structure is actually unique to each of these seeds. It's a unique representation learned by these models. So this is different random seeds. You can do this sort of same analysis for different model architectures. And again, there's sort of this difference between things that have the block structure and things that don't have the block structure. Okay. So to summarize things, sort of so far, we've kind of been varying the kind of depth and width of these different models by sort of analyzing their internals. We've gotten sort of this characteristic property of their representations for these large capacity models, this block structure, and we've also gone on to try and understand, you know, how this affects sort of representations learned across different models, and come to this conclusion that well, do wide and deep networks learn the same things? Well, they learn the same things when they don't have a block structure, but when they do have a block structure, you are seeing that there's some unique set of features learned by each model. So to complete this study, we actually returned to thinking about the actual predictions of the model. So, you know, we're typically evaluating the model just by looking at its output. And so as sort of a final kind of question, we wanted to understand whether there were clear differences in the actual predictions and errors being made by models that had different architectural structures. And so to do this final study, what we were doing is we were training a population of networks that had a certain architecture on some task, and then we were comparing to a population of networks also trained on that task, but maybe with a different architecture. And so the important kind of quantitative thing to note here is that when you have a population of architectures trained on some task, say architecture A, we can actually think about the accuracy of that population. So we can take a particular data point and then we can compute, say, PA of X, which is the sort of probability that everything with architecture A classifies X correctly. And same for B, and you can do this at a class level also. So there are sort of two different kind of granularities here. There's at a data point level and at a class level. Okay, and so sort of with these populations trained, we looked at comparing accuracies and errors at a data point level and at a class level. And so the results actually varied a little bit on the data sets. So on CFAR10, we didn't really see any statistically significant class level differences. But when we looked at the per example level, we did see that architectures that are more similar in structure have actually more similar predictions. So here, sort of on the X and Y axes, we are precisely plotting this sort of PA of X and sort of PB of X for every single one of these data points X. And so on sort of the left plot here, we're kind of comparing a deep network with a wide network. And you can see that things are very far out from sort of the Y equals X line. So there are lots of data points which have a very different sort of accuracy for architecture A compared to architecture B. Whereas in comparison, when you compare a deep architecture to a deep architecture or wide architecture to a wide architecture, things are much more concentrated along the Y equals X line. And there are many more experiments here that are in our paper, so do check it out. And then finally, on ImageNet, what was interesting is that we saw class and example level differences. And because there were sort of these class level differences, we were actually able to identify some characteristic errors. So over here along the x-axis, sort of, well, we have sort of a very deep network again and sort of a wide network. The dots in orange are sort of a baseline, so they're sort of just the deep network minus the deep network, whereas the dots in blue are sort of the actual result we care about measuring. They're sort of the population accuracy of the wide network, subtracting the population accuracy of the deep network. So sort of translating all of that, things sort of, so things with sort of positive Y value are places where the wide model is doing better. And things with sort of negative Y value are places where the deep model is doing better. And so here we're sort of broadly seeing this interesting bias where maybe the wide model is doing a little bit better on scenes, whereas the deep model is doing better on objects. Okay, so.
Maithra, a quick question from YouTube, from Tyler. Back one slide, were the deep and wide experiments on ResNets with different seeds?
Yes, yeah.
So they have the same architecture, just different seeds.
Yeah, so in this case, it's sort of same architecture as different seeds, and you're sort of seeing the amounts of variance you'd naturally get thanks to sort of just like, I guess, sort of sampling differences. But in the paper, we sort of, they just didn't fit on the slides, but we have this nice interpolation going from sort of things that are sort of like very deep versus things that are sort of very wide, and sort of what does the spread look like. And what you can broadly see is that architectures that are sort of both kind of might classify as deep, but not the same architecture, do look a bit more concentrated along the y equals x line than kind of going from the deep to like the very sort of wide architecture, for instance.
Got it. That's a great experiment. Thanks for sharing.
Okay, so back to this. So to summarize, in ImageNet, I think the interesting kind of addition was sort of this class level difference. And so I'll just sort of summarize. Sort of again, as kind of broader motivation, we kind of this was sort of really inspired by the fact that we really need measures that give us more insights into the internals of these systems to really help inform sort of principled and robust design processes. That sort of really motivated a whole line of work, including CKA, that we use to sort of study, give us insights into internals of these systems through representational similarity. And this was kind of really the tool we used to study lots of properties of networks as we varied their width and depth. Specifically, we sort of saw this block structure component in networks of large capacity. We're able to kind of really interventionally link that to the capacity of the network. And most sort of satisfyingly, I guess, we're really able to pinpoint what this block structure does functionally. It sort of preserves and propagates this first principle component. And this turns out to be very important when we think about what's going on across different models. Model architectures that without the block structure do share features, but the block structure is sort of uniquely learned to each model. And we also observe these sorts of differences in actual predictions, which are influenced by like the actual architecture of the model. And on ImageNet, these sorts of characteristic errors. So that's some of the things we covered. I think there are lots of really exciting open questions in this space. So firstly, I think there's a big open question on the dynamics of the block structure. So how is it really learned? And sort of like, how does it evolve and sort of how stable is it? Things like that. There are sort of nice questions on other architectures and other tasks. We informally got told that the block structure has also been observed in things like transformers, and I think it would be really interesting to investigate that. And then there are sort of questions, again, maybe related to the block structure on sort of, is this sort of an overfitting thing? Is this a key feature? Sort of why does it exist, basically? Okay, and so with that, I will wrap up. Thanks everybody for tuning in. And I guess, Charles, you might have some questions.
Yeah, I'll take a few minutes to ask you some questions. Want to make sure that we get a chance folks who are online can ask questions in the Zoom as well. I guess my first question is, so you partly addressed this by mentioning transformers. How much do you think that this block structure propagating this first principal component of the gram matrix, do you think that that's really a ResNet specific thing because they have this capacity to just pass information through an identity transformation? Or do you think that that's something that you might observe in, say, like a VGG type architecture?
Yeah, so the reason we focused on ResNets is because like kind of these skip connections are really sort of useful and important for, I guess, stabilizing things as you go deeper. But in the paper, we actually have additional results sort of without the residual connections and stuff, and you do take a bit of a performance hit. But on the other hand, you do see the same sort of thing with the block structure. And sort of, yeah, like those sort of very similar properties. So I do think, and especially given sort of, this is informal, so I think this is a definite exciting open question that would be really cool to go after. But I think, transformers would be great to look at. And the fact that somebody informally said that they think they'd seen something like that in transformers. So I think that would be a really nice sort of thing to verify on.
Yeah, that's cool. I think my current mental model for transformers comes from that hop field is all you need paper, that like a lot of what's going on there, like some of the pieces, the attention heads are kind of pulling out averages, and then some of them are pulling out more fine-grained information. It'd be interesting to see if there's a connection between that idea and what's going on here.
Right. Yeah, definitely.
What other hyperparameters? It seems like you may have sort of fixed a lot of the hyperparameters besides the width and depth. So things like how many max pools and comms you're doing, the kernel sizes, whether you're using batch norm, when you're using it. Do you think any of those other kinds of hyperparameters that are maybe not quite as architectural still impact maybe the block structure or other factors about representations? Or do you think that this is something that's going to stay the same no matter what you change there?
Yeah, that's a good question. So I think some things like probably batch norm, my prior would be like they don't necessarily have to affect things too much. So our goal is, so we want to vary within depth because that felt like a number of sort of things that, you know, were manageable to like vary and sort of do experiments with. And then we kind of want to keep everything else stable. I think other kind of design things, yeah, the other next kind of thing to look at on the vision side would be sort of like maybe things like kernel size or like kind of receptive field size. I guess this is kind of stepping into the data, the actual input data itself, but you could look at kind of playing with the resolution of the input data, for instance, and try and understand whether sort of how that affects things. My hypothesis would be that like somehow if increasing the resolution of the data somehow, you know, really inflating the kind of effective data set size, then I think, you know, you might need sort of larger models before you start seeing the block structure. But I think otherwise I would still sort of expect to see something like this.
Mm-hmm. One idea that's come out of the neural tangent kernel literature and the people thinking about like scaling limits of neural networks is
Uh-huh.
that it's very easy to end up with a really big neural network that ends up collapsing down to a kernel
Right,
machine where
right,
it's really effectively, it's like you're only training that last
right,
linear readout layer.
right,
Do you think
right.
there might be a connection between what you're seeing with these big block sizes that seem to be maybe a collapse in the representation and that idea? Or do you think those are unrelated?
So I'm not sure. So like you'll have to tell me because I haven't been following that literature sort of extremely closely as of late. But I
Mm,
also thought you took like a little bit of a performance hit when you sort of did that. And I need to check because I know it varies also depending on the architecture. Like maybe
mm,
convolutional networks, you maybe see a performance hit, but then maybe for fully connected models, you don't. And then like there's a ton of work out there. But
mm,
here, I think they might be different things because I think here, like you're not like I don't think you're sort of just starting with this and it's sort of like you're just not sort of like, you know, it's sort of not training at all. I think it's more sort of like the somehow something about the dynamics of learning is resulting in sort of this sort of propagation sort of happening.
mm.
So I think those would be different, but that's also an interesting question, so that's worth investigating. But oh yeah, sorry, one other thing is just, yeah, so the other motivation for doing this is that, so you know, like I guess back on some work on like expressiveness and stuff, depth and width are sort of these parameters that we've sort of mathematically studied in various ways. Like you randomly initialize a network and like look at its depth and width and understand what's expressive, what's efficient to express for models of different architectures. But sort of the real motivation for doing this was, can we just take a bunch of models that are sort of very close to like what people would kind of be tempted to do in practice if they wanted to increase model capacity or something, and can we test them out and sort of then understand what's happening with their representations. So indeed, I think one really cool thing to me is that a whole bunch of these architectures that we tried with sort of varying depth and width, like performance-wise, they really look pretty identical. And it's only probing into the representations that you sort of see this property. So that was really cool to me.
Mhm. Yeah, that is interesting that you see like the top line accuracy can be very similar, but then the classes on which they're getting the best accuracy and the worst accuracy look different. That's a really cool result.
Yeah, yeah, yeah.
All right. Well, that's all the time we have for our first talk. So thanks a lot, Maitra, for coming through and answering folks' questions and doing some really excellent work.
Okay, thank you so much.